Recording is rolling. It is Wednesday, September 11th. So agenda today, guys, double check focus. You guys know that there's a score report coming out pretty soon. So today's the end of a certain grading period. Teachers have a couple days to get grades in. Double check focus. Make sure you don't have anything that says NTI. That would stand for not turned in. I really want to get you guys' quizzes back to you, but I can't hand those back until I have them all in first. So as of this morning, I'm looking for 4 quizzes from AP, 3 from honors, and 3 from conceptual. When I get all those in, that I can score them all, hand them back, and you guys can see exactly which ones you missed, what the correct answers are. Okay. All right, so let's go. Today, we're going to pull a couple of questions from this Paul Hewitt book for you guys, and then oh yeah, I'm looking around the room. You guys already have this page out. We're going to solve some of these later today. Here we go. That is the plan. All right, so challenge questions from this book. Got a boy on a tower throws a ball 20 meters downrange as shown. Okay, so got a 5-meter tall tower about. Looks like he throws it straight horizontally and lands, bam, 20 meters down range. Aha. What is his pitching speed? Who knows? How fast did he throw that ball? How about this? You have to think what's going on vertically, what's going on horizontally, put these two ideas together. Okay. Guys, a 5-meter tall tower, how much time would it take for something to fall down in 1 meter? How much? All right, sorry, what did I just say? I meant 5 meters. Right. How much time would it take to fall 5 meters? How much time is that? 1 second, right? Oh, hey, you know what? Yesterday, when you guys were firing those launchers off the balcony, was that balcony about this tall? It was about 4 or 5 meters tall. It'd take about a second to fall down that height, right? Okay, so it's going to take approximately a second to fall. And then when we went 20 meters down range before it crash landed, then how fast was it going across the field the whole time? Didn't it go these 20 meters across during that 1 second of falling? Did he have to throw it at 20 meters per second? That's the answer, 20 meters per second. The answer is 20 meters per second. How many guys notice that that is exactly yesterday's lab? That is yesterday's lab right there. Okay? If you want to see the full fancy answer in terms of variables, be like this. Right? So to fall 5 meters takes 1 second. So get 1 second here. Went 20 meters across the field during that 1 second. 20 over 1, 20 meters per second. That's it. That's the whole thing. Okay? That's it. He's really using 4.9 meter tall tower because if you set Earth's gravity field to 9.8 meters per second squared, it's more precisely correct. All right, so you guys good with that? All right, I got another challenge question for you guys. I got a zookeeper devises a rubber band gun to shoot a banana to a monkey. So we got, here's a slingshot with a banana. Here's a monkey who's too shy to come down from the trees. If the monkey does not move, should the keeper aim above, at, or below the monkey? Let's see, show of hands. How should he aim this banana? How many guys say he should aim, say, like above the monkey? Who says above the monkey? Yeah, you guys all say that? Right, because, okay, so that if there's gravity field, then that banana is going to go down to parabola path and possibly get to the monkey. Right? Now, how far above the dash line? Well, it depends on a bunch of variables. How far away from the tree is he? How high up is the monkey? How fast is he shooting with the slingshot, the banana? For that matter, gravity field can matter too. Guys, what if you turn gravity off? Turn gravity off. If there's no gravity, then you should aim which way? Straight at the monkey, because now the banana just goes in a straight line. But if you turn gravity back on, now definitely something to do with above the dash line. And how much above? Well, you need some numbers to do some math. Okay, now here's a really tricky question. You guys ready for a tricky question? I'll give you guys a little time to think about this one. If the monkey lets go of the branch at the instant the keeper shoots the banana, so they let go at the same time. let go at the same time. In that case, should the keeper have aimed above, at, or below the monkey so that the monkey gets the banana while the monkey is still falling in midair? Right? So part of this to make this work is before the monkey hits the ground. Right? Now, help you guys out a little bit here. Think about this. The monkey might catch the banana at different locations depending on maybe how fast he shoots it. Right? So if he shoots it kind of fast, maybe the banana gets to the monkey right about here. Or if he kind of lobs it, maybe it's like kind of down here or down here. Right? But before the monkey hits the ground, so that the banana is still following a parabola type path, like a projectile. Right? All right. Give you guys a little time to think about that one. This one you have to think pretty deep on. Might be a good opportunity to get some paper if you need some paper. You guys have some notes out, whatnot. All right. So see, show of hands. And you guys see, of course, the three options there, A, B, and C. Is it above, at, or below the monkey? What do you have to aim at? All right, you guys ready for a show of hands? All right, here we go. All right, how many guys think that the keeper should still aim above the monkey like before? Who says above? Nobody says that. All right. Who says you should aim right at the monkey? Right at the monkey. Ooh, okay. I see some votes. How many say below the monkey? Who says below the monkey? Okay. I see some votes there too. I think most of you guys said at the monkey, which is actually the correct answer, right? Which is really good because my earlier classes, so far today, it's been pretty much a 50-50 split between at or below, right? But yeah, the answer is at. Now, why would you aim at the monkey? Right. Why? Right. Remember, you're letting go of the banana at the same time the monkey's letting go of the tree branch. Right. Well, let's start with the monkey falling. The monkey lets go of the branch and starts falling straight down. Now, how far would the monkey fall as a function of time? Would that be h equals 1/2 gt squared? Is that right? 1/2 gt squared tells you how far the monkey is falling. Right? Right. How about from the banana point of view? Right. Now, if there is no gravity, let's turn gravity off just for a moment. Do you guys remember if you aim right at the monkey, it'll follow the dashed line? Actually, that would give you the answer, at least for that specific case. If there's no gravity field, you would definitely aim right at the monkey. Monkey lets go, the branch doesn't move. The banana, straight line path, straight towards the monkey. Gets the banana. Now let's turn gravity back on. Right? Well, now the banana is not going to follow this straight dash line path. It's going to deviate and follow, well, one of these projectile paths, right? One of these parabola paths, right? Depending on, did you shoot it really fast? Did you kind of lob it? Right? So one of those, right? But each of these projectile paths, parabola paths, is going to deviate from this original dashed line path by guess how much? 1/2 gt squared. If you want to see a full formula, we're really playing off this first kinematic formula right here. Okay. So in place of this general displacement, you can call this like height, like how high is the banana, right? Elevation. Right? Here's, okay, if there was no gravity field, it'd just be some version of that. Right? And if you put gravity back in, then you could call this minus 1/2 gt squared. And this bit is how much is deviating from that dashed line path, which is also exactly matching how far the monkey is falling. It's the same vertical change, right? Yeah. So gotta aim right at the monkey. Aim right at the monkey. Right, you guys good with aim right at the monkey? All right. All right. I want to take some things. All right. Let's solve some puzzles. It's puzzle time. All right, you guys got this page out, ready to go. All right, what I want to do with you guys is, okay, there's a bunch of scenarios on the front, and there's some scenarios on the back. Here's my goal today, is to take you guys through the first scenario. That's number 1 through 4. We'll do that. Right. That involves a cannon at the edge of a cliff aimed horizontally. Hey, just like your guys' lab setup yesterday. Later on in class today, we'll do number 11 through 14. That is a different setup. It involves a cannon on a plane that's ramped up at some angle. So that'd be one of those. Right? And then the ones on the back is kind of a hybrid. Yes, there's a cannon on a cliff, but it's also ramped up at some angle. I want to do this one on the top right with you guys, but that'll be near the end of class. Okay. All right, so first scenario, number 1 through 4. A cannon fires a cannonball horizontally at given horizontal velocity from the edge of a cliff. Ooh, I gave you guys some information in a table down here. With that in a moment. The cannonball lands some displacement away from the base of the cliff. How much time did that take? What's the height of the cliff? Oh, we don't even know the height of the cliff on number one. Maybe some of these other ones, but not this one quite yet. And there's also a couple of questions about the crash velocity. So we'll get to those way later on. So this is number 1 through 4. Right, number 1 through 4. All right. You guys, of course, got some paper out, some notes. Set up a cliff here. Put a cannon right at the edge. Blast this horizontally. I'll call it, it's okay if I call this V sub X because it's the blast velocity, but the fact that it's aimed horizontally, isn't that also the horizontal component of velocity during the entire flight? Right? That's gonna maybe hit somewhere down there about something like that. What else did okay, I told you this blast velocity. Now my paper says I have 190 meters per second. 190 meters per second. Okay. I told you where the ball landed, crash landed, pow, down here. So maybe I'll call this X equals, and my paper says 295 meters. Okay. Also in the corner of my paper, I'm going to write G for gravity field equals, on this paper, I was using 9.8 meters per second squared. So that's what we'll use today. Right? And that's pretty much it. That's what you start out with. Right? That's just enough information where you can solve everything. You can solve for the time, you can solve the height of the cliff, you can solve just from this too. You can solve things about crash velocity. All right, now before I go plug in and chug and make, I want you guys to see how this page is organized. This is true for these first 6 scenarios here. Right? You guys see how there's like this double table? There's a left half of the table and a right half of the table. Is that right? So what I'm trying to do is give you a framework how to categorize these variables. Right? Oh, the short looking half of the table, there's 3 possible variables that you're juggling, which means it has to be horizontal information. You guys see I wrote horizontal right there? Horizontal, maybe that helps too if you write that on your paper. Okay? Because horizontally, there's only x equals vt. Right? There is no acceleration horizontally. Gravity doesn't pull horizontally. There might be a little air drag, but we'll call that negligible. So we're going to say no air drag. Okay. Now, vertically, it's a different story. Vertically, now we're juggling 5 variables. And this could be any of those 3 kinematic formulas. We'll have to go equation chopping, maybe. The fact that gravity pulls vertically means there's an acceleration, which means the velocity is always changing. Okay. Now, all these variables are vector values, which means that they have spatial directions, which means they're either strictly horizontal or strictly vertical, except for one. Guys, there's one variable that's a scalar, which means it does not have a spatial direction. Which variable is that? What's the only variable that does not have a spatial direction? Time. Yeah, time. Yeah. Right. What that means is if you solve for time either horizontally or vertically, it's going to be the same time. That's the only variable that you're allowed to transfer from one half to the other half of the table. In this case, you guys have noticed for the last 3 weeks, we're always going from some point A to some point B. In this case, from the edge of the cliff down to the crash point, down to the valley. Okay. Whether you analyze it horizontally or vertically, either way, it's the same time. You see it? Okay. And you guys remember that there's a minimum amount of information to solve anything. Like with the 5 variables, well, you have to have 3 to solve it. With the 3 variables, well, you have to have 2. So give you guys a little checklist. Right? This is just one way to frame the question. Right? So if you're going through and say, well, what information do you have? Should I start with vertical or horizontal? Okay. Now, in this case, you guys are loaded up with horizontal information. I know how far the ball goes across because I saw exactly where it crash landed. It's like yesterday, you guys maybe took the trundle wheel or a meter stick, version how far. Right? And I also know the blast speed. I'm giving you guys that too. Right? So, guys, what formula should I use to kickstart this whole process? There's only one formula horizontally, and that's what? x equals v sub x times t. That's it. Right? It's going across the field some distance at some speed for some time. Right? There's no accelerations. You don't have to say, well, which kinematic formula would it be? There's only one you could use. And we know two of these variables. I'm trying to figure out how much time, because I know how far and I know how fast. Okay, this is strictly across the field. It says here, if I draw a little hot air balloon up in the air, this is the reason I draw this is as if you're looking straight down on the situation, you're seeing all horizontal type information. No, it's pretty much constant speed across the field. Can you guys solve this in terms of variables? The time it takes to get there is how far divided by how fast. Boom, boom. You guys can do that? Let's get some numbers. So on my paper, now careful because your numbers are probably different than mine. Mine's going 295 meters across the field at a rate of 190 meters per second. Getting there. Divide that out. So the time is this many seconds. You know, keep an extra digit here. That many seconds. That's a crazy amount of precision, but maybe I'll say by rounding for the end. All right, I think it's number one right there. Yeah, number one. I see an answer choice that aligns with that, so we're all good. Right, you guys got number one in your paper? Okay. Now remember, time is the scalar value. That means it also applies in the vertical analysis. Hey, that means we have three kinematic variables on the vertical part of the table, which means we can solve that now. Now we can break out those three kinematic formulas and start solving these and solve a bunch of other stuff. Of course, these are all going to be vertically oriented because gravity is pulling vertically. Right? So I need to solve the height of the cliff. And I just found the time. Ooh, guys, if you want height and you have time, it's accelerating. What formula does that sound like? Does that sound like, here, if I call this H, could that be H equals V naught YT plus 1/2 GT squared? Be like that? Some version of that. Right? How far does the cannonball fall? If I call it down the positive direction, okay, then the cannonball is moving in the positive direction vertically, and also gravity is pulling positive. It's all positive, all positive. Okay. Oh, you know, I don't even need the whole thing. I can actually simplify this. Guys, how can I simplify this? If I blast the cannonball horizontally, then right when the cannonball is leaving that cannon barrel, how fast is it moving up and down? 0 meters per second, which means this term goes away. All I really need is this. H equals 1/2 GT squared. Okay, that's all you need. Okay. As long as either you drop the ball or throw it horizontally, that's true. You guys remember that? If you throw the ball horizontally and you drop the ball, do they have the exact same vertical motion, hit the ground at the same time? So let's get some numbers here. We're using on this paper 9.8 meters per second squared for gravity field. I can plug in the fall time that I just found. And don't forget to square the time. Square the time, right? Let's see, it's 1/2 G T squared. All right, that'll tell me the height of the cliff. That is this many meters right there. I can believe that. Looks about right. And if I had a 5-meter tall cliff, it would have taken a second. If I had a 20-meter tall cliff, that would be 2 seconds. Yeah, that's right, I think. All right, guys good? All right, the next couple questions have to do with this crash point here. So if I hold my ruler flush to the curve, see I'm holding my ruler flush to the curve, moving along the curve, right? It says something about the direction of its velocity, which is always changing a little bit as it's in motion, right? But right at that crash point, right at that crash point. It can have this crash velocity vector. So here comes this cannonball, boom, crash landed right there. I say it could be like V crash right there. Okay, I'll label it that. Close. V crash. That's question number 4, by the way. But okay. But I can break this into components. I can say, well, that cannonball is kind of moving across the field, and it's kind of coming down at the same time. You see how I just dashed off the components? Right? How fast across? How fast down? Right? I can label this V sub x and V final in the y direction. V sub x and VFY. Got it. Separate this out here. Okay. All right. You guys all right? Oh, and you know what? One of these you already know. Because which one of these do you already know? Aha, V sub x. Yeah, because that is the same thing as the blast speed from the cannon. It's been doing that the whole time. So you just copy paste that number right there. It's been going 190 meters per second all the way across the field, horizontally. Now vertically, it's a different story. Vertically, it's been picking up speed. I can think of 2 different ways to get this final velocity in the y direction. I could either play off the height of the cliff and pull out that third kinematic formula, v squared equals b naught squared plus 2ax. Yeah, play off the height of them. Or I could play off the fall time and use the second kinematic formula. I think that's what I'm going to do. It's a little easier. Can I just go g times t? Do that. So gravity's pulling 9.8 meters per second squared, and it does that for this many seconds. See what is that? GT. All right, that should be the answer to number 3. So you got number 1, number 2, number 3. All right. You guys getting answer choices that are multiple choice answers on your paper? All right. That's all working out. Question number 4 says, what is the total crash speed? So that's like if the cannonball is about to crash land on the ground, it's coming in at this angle. If you point a radar gun at it, that radar gun's going to tell you the total speed. Ooh, I bet you guys can figure this out. How can you figure out how fast in total the cannonball is coming down? If you know it's going this fast across, it's coming this fast down. You guys see 2 legs of a right triangle? And you're solving for the hypotenuse? That's a job for the what? Pythagorean theorem. Pythagorean theorem time. So I'm going to cut straight to that and say V crash. I'll write that out. I'll write Pythagorean theorem. A little abbreviation there. V crash equals the square root of a squared plus b squared. So let's go that many meters per second being squared plus that many meters per second being squared, the square root of the whole thing. That's Pythagorean theorem right there. Let's try that. Square root of a squared plus b squared and there's number 4. You guys got that too? Get multiple choice answer. It's all good. All right, I think some of you guys got that. Some guys, while you're wrapping that up, throw in one more detail, which is if you want to turn this crash speed into a crash velocity, can I do that by getting, what is this angle here? Supposed to call it theta. Here, I think I got a space on this side of the paper right here. Okay. Do you guys know how to get this angle theta? Like the crash angle? Inverse tan, inverse tan. I'll do, well, opposite over adjacent. So it'd be Vx over Vfy. Pop those numbers in. It'll tell you exactly how many degrees it's coming in. You do that too? All right. All right, you guys good? All right, next scenario. Okay, I'm gonna pick a different paper. Yeah, here we go. I still got new paper. So this paper's a little different. Let's do number 11 through 14 right here. 11 through 14. Got a cannonball fired. Okay, at some speed. It's some angle, so many degrees above the horizontal on a flat plane. Okay, this is a different type scenario. I think I solved one the other day. It was kind of like this. So find what's the horizontal and vertical components of velocity. How much time did it take? Like what's the hang time? And then how far did the cannonball go? So what's the range? The horizontal displacement. So get a picture going. This is number 11 through 14. 11 through 14. The big old horizontal plane. Set up a cannon right here. Blast it up at some angle. So I'll say V blast. Okay. Now this number I gave you. So the paper I'm looking at right now says this many meters per second. Okay, so we got that. Okay. I told you the angle from the horizontal. The paper I'm looking at says this many degrees. Okay, my picture's not exactly to scale, but you guys get the idea. Like that. And pow. Then cannonball flies off. Make sure I'm getting this. All right. Something like that. And pow. Right, and it's over here. Okay. Off of the corner, I'm going to write G equals 9.8 meters per second squared. And I'll write the word down. Okay. Because we're going to have competing directions going on with this one. Because if I'm blasting the cannonball kind of upish and gravity's pulling down, do you think there has to be a negative sign somewhere? There's going to be opposite directions. It's going to be a negative. Okay. So I did on your guys' paper print G is negative 9.8 meters per second squared. And that's actually, I'm going to use it in the formulas. Okay. So it looks like I'm calling up positive and down negative. You see it? Okay. So yeah, so as I'm solving this, I use that same convention. Oh, look at the other number I also typed in your table. Do you guys see y equals 0 meters? Is that one too? Okay, that's a vertical displacement. You guys have noticed for all these puzzles we've been solving for the last few weeks, we're always going from some point A to some point B. Now, if the point A is the point of the cannon, the point B is the crash point. You're going from the ground to the ground. Guys, what is the vertical displacement from the ground back to the ground? 0. Right, that's why it's 0. Okay. Okay, so yeah, so I typed that number, but got that too. So, no, all these things. So first couple questions, number 11 and 12 says, what's the components on this velocity? So I'm going to break this blast velocity into components. Say, well, how fast across and how fast up? I'll call this V sub x. And I'll call this V naught y. And how do you solve these? Because V sub x, that's equal to what times what? Who remembers this? Okay, so I'm going to start with the full blast speed, 90 meters per second, and multiply that by what, sine or cosine of 25 degrees? Which one is it? Cosine. Cosine. 25 degrees. Right? See what we're trying to do. We're trying to translate from the hypotenuse of a right triangle to the leg that's adjacent to the reference angle. That's a cosine relationship. So the full blast speed times cosine of that reference angle. I'm getting this many meters per second. Okay. All right, so that's how fast the cannonball is going across the field. And that should be true the entire way across. Now I'll go back to draw this little hot air balloon again, just to emphasize this point. Got a hot air balloon up here. Right, somebody's looking straight down on this scenario. Okay. And to them, looking straight down, okay, looks like the cannonball is always going across the field at, well, in my case, 81.6 meters per second. That's true the entire way across. It's not speeding up or slowing down horizontally. Now, vertically, it's a different story because gravity is pulling vertically. Right? So let's get the initial value. Right? Notice in the y direction, I got two subscripts because it's not just plain vertical, but it's also initially. So it's always going to change. Well, if this other one was a cosine relationship, you guys think this one's going to be the sine relationship? Let's go the full blast speed times sine of the reference angle of 25 degrees. The calculator, scroll up, scroll over, pop in a sine where the cosine used to be. I'm getting this many meters per second right there. That's number 11 and number 12. You guys get number 11, number 12? Working out? All right, very good, very good. Oh, next question is, what's the total hang time? Right, how much time for this whole thing to happen? Okay. I can think of a few different ways to do this. And the other day when I saw the similar puzzle, I showed you guys multiple ways to do this also. Okay. So here's one way you could do this. Do you guys remember the vertical displacement from beginning to end is 0? Right, starts at the ground and at the ground. Okay, you could pull out the first kinematic formula and solve it that way. Another way you could do this, and I think what I'm about to do here, is you could break this puzzle in half. Guys, could I solve for how much time it takes to get to the top point? And then, if it takes so many seconds to get up to the top, do you think it takes the same number of seconds to come back down? It's by symmetry. So however many seconds that is to the top, I can just double it and get the full hang time. Right. Let me try that method. I've been doing that method today, so that one's pretty fun. Now, if I do that method, I have to pull out the second kinematic formula. So it goes like this. V final in the y direction equals V initial in the y direction. I'm going to say minus GT. Okay. Something like that. Right, is that all right? All right, again, playing off this particular method, is what is the vertical component of velocity of the ball at the very top? 0. Yeah, right. Now it's moving to the side, but it's not moving up or down for 1 instant at the very top. That's that number right there. 0 meters per second at the very top. Okay. And once I plug that in, I know that I'm only solving for half of the hang time. So I'm going to specify that too. So I got, you guys know what number goes right there? Oops. That many meters per second on my paper. It's the initial component of vertical component of velocity. Right there. Then minus, now on this paper I was using 9.8 meters per second squared for gravity field. And then t, I can solve for t, but I'm going to throw a subscript on this t. I'm going to say half of the total hang time, so that when I get some number of seconds out of this, I can remind myself, oh yeah, that's right. That's not the full story. It's only half the story. So that I can double it to get back to the full story. All right, guys, get that? Right. Again, not the only way to do it. Maybe you're leafing back through your notes from a few days ago saying, oh, I know a different way I want to do this. As long as you get that multiple choice answer. All right, different ways to get to the answer. All right, so here I'm going to add this over to the other side. Throw a little algebra step right here. All right. Then divide both sides by this coefficient, which is free fall gravity. See what I'm getting. What is that? Divided by that. I'm getting T half is this many, guys, this many what? What's the unit? Is it seconds? You guys count time in seconds? Yeah. I'm just saying, grading all my classes papers over the last few days. More students are getting better and better at units, but I've still got some students quantifying time in like meters per second squared, or like how tall is the cliff? Oh, so many meters per second is how tall is the cliff? So you guys know height is in meters, time is in seconds. You guys know this, right? So right there's the end. Oh, sorry, no, I'm not done yet. I'm not done yet. Okay, guys, if it takes 3 seconds to get to the top, you think it takes another 3 seconds to come back down? Okay. So if I want the full hang time, do I have to double that number right there? So times 2. All right, now we're back in shape. Yeah. This many seconds. Okay, that's the answer to number 13. It's number 13 right there. It's the full hang time. Okay, you guys getting a multiple choice answer on number 13 that matches your work? So yeah. All right. One question to go. How far down range does that ball land? So now we're going to switch back to horizontal. We've been doing vertical for a while, right? Because you guys know vertical information would constrain how much time it can be in the air for. Right? We've got gravity pull in, we got some kind of constraint, right? But now we're going to say, where does it land downrange? That's a horizontal question. Because there's only one equation I can even choose for horizontal motion for projectiles. What's that one equation? X equals v sub x times t. That's it. Right? I don't have to go equation shopping. Which of the 3 kinematic equations? No, because there's no acceleration. So it's just distance equals speed times time. That's it. Now I got to make sure I'm plugging in the right numbers, of course. Okay. So, guys, how fast is my cannonball going across the field? That one right there. That fast across the field for this total hang time. At many meters? Yeah, see an answer choice that says exactly that number of meters, and it would be meters, wouldn't it? Because we're talking about a horizontal displacement, talking about a distance. All right. Working out for you guys too. Let's go back. All right. So what we did here, the first thing we did was we found a couple of components: horizontal component of velocity, vertical component of velocity. Okay. Once you know, especially the vertical constraints, you can go here and solve for hang time. Okay. There's different ways to do it. I picked a method where I broke the puzzle in half and then went back and doubled it at the end. Okay. After you get that, you know how much time, you can say, oh, well, I know how fast it's going across, times how much time. We'll tell you exactly where it lands. Boom, boom, boom. Just like that. All right, guys able to do that? I want to do a little side quest here. Let me check this, because I've been making the claim that this should also work. We go back and plug in Let's see if this method works. So how far downrange it lands. We've got the blast speed squared, so that was 90 meters per second. Square that, divide by, say, 9.8 meters per second squared. They throw all that in parentheses. Parentheses, group that together. Okay. Then times sine of double angle. So 2 times, my angle was 25 degrees. So double that. Okay. Okay. I should get 633. All right, let's see. You guys ready? Moment of truth. 633. Come on. Oh yeah, it's 633. Yeah, look at that. Okay, so my posters work again. Oh yeah. All right, you guys good there? All right, so let's do one more scenario. I'm gonna pick one from the back. So we did this scenario here. We did this scenario here. Let's flip over to the back. Now, all the ones on the back are really similar setup. Oh, yeah, we got a cannon on a cliff that's also ramped up at some angle. And for every one of these, I told you gravity field. It looks like I see Earth gravity all over the place. I told you the height of the cliff. I told you the ramp angle. Okay. And I also told you the blast speed of the cannon. Right? So if you know all those things, and it looks like where I'm going with this is how far away from the base of the cliff does the ball land? Right? That question shows up on all three. Okay? The very first scenario, I really help you guys out a lot because I take you guys through step by step. Find the components of velocity, find the hang time, and then you can find how far away it lands. Oh, and it's multiple choice. That's nice. Okay. This one on the top right, you don't get the multiple choice or anything. So I'm going to walk you guys through this one right here. Okay. You guys ready for this one on the top right? Of course, I'm just using the numbers on my paper, probably different than your numbers anyway. Okay. So, this will be able to answer all of them, really. Okay. So okay. Let's get draw this picture. So I need cannon on a cliff. Okay. My notes from earlier. Sure, I fit these notes. Like I can fit them all on one page. Just gotta make sure I'm spacing this out right. So looks nice. Okay, so cannon on a cliff. Right. Blast up at some angle. I call this V blast. Right, I'll put a number there in a minute. It's gonna pop. So something about like that. I'll land over here. All right, so let's set up. I'm going to in the corner write G equals 9.8 meters per second squared down. So I got that. Right. So back to this blast velocity. So my paper says 64 meters per second at a 40-degree angle from the horizontal, above the horizontal. So you guys know one of the steps is I'm going to break this into components. So start to draw it that way. Right? You guys see I'm dashing off some components. Right? It's going up and to the right. How much up? How much to the right? Well, I know this is going to be a 40-degree angle. So I got that. And oh, I also told you the height of the cliff. That's the other number you need. So I'll say H equals, now my cliff is 15 meters tall. All right, there you go. So with just that, there's enough information here where I can solve everything. So I think you guys have been through enough of these so far to figure out, okay, we're going to find out what are these velocity components, V sub x and V naught y. Okay. After that, I'll be able to find what is the hang time. And after that, I can go back to horizontal and figure out how far away. Boom, boom, boom. Okay, see, roadmap. All right, so start with these components. Okay. Guys, V sub x, how can I get that? What times what? Take my full blast velocity, 64 meters per second, and multiply by what? Aha, cosine. Yeah, cosine of 40 degrees. Oops. Lost track of, okay, all right. $64 cosine 40. So this is 49.0 meters per second. Okay, and circle that, hold on to that. It'll be an important number. Okay. Do you guys think initial vertical component of velocity is just the sine version of that? Again, so do 64 meters per second times sine 40 degrees. Let's see, scroll up, scroll over where the cosine was, pop in a sine. That's looking like 41.1 meters per second. And circle that, hold on to that. Point. Okay, so I got my velocity components. I know what's going on at the blast point of the cannon. Yeah. Of course, that horizontal component of velocity is going to be the same all the way across the field. And then this is probably going to enter into my very final calculation. Okay. This vertical component of velocity, I know, is always changing. So 41.1 meters per second initially, but then gravity pulls down. Right. All right. Well, guys, to figure out the total hang time from this point to this point, the total hang time, isn't that going to be constrained by the height of the cliff and the gravity field? Oh, yeah. Or is it possible? Oh, yeah, could these be the same? Guys, these will be the same if you have a what degree angle? 45. Yeah, if you have a 45-degree angle, true, these would be the same. Yeah, they're true. All right. So I need to solve for time and something to do with the height change, the height of the cliff matters. That can only be which kinematic formula deals with both height and time for an accelerating situation. It's got to be the first one. Yeah, got to be the first one. Right. Here's a general displacement, but you guys know I could put h right here, like a height change, something like that. H or y, we can call it. Okay. So here, I'll say h equals v naught y t. And depending on how you think of it, you say plus 1/2 at squared or minus 1/2 gt squared, some version of that. Okay. But here, you're going to have to be careful with positive and negative signs because we got two different directions going on. I'm kind of blasting the cannonball up-ish, gravity's pulling down. Ooh, guys, what about the displacement of the ball from the top edge of the cliff down to the ground? That's also which way, up or down? Down. Okay, so I'm gonna have to be careful about what's positive and what's negative. You guys see that? Right. Suppose I call up positive. If up is positive and down is negative, if I do that, then in place of this h, going from the top of the cliff down to the bottom, should I put in positive or negative 15 meters? That would be negative. Do you see that? Right, as long as I define down as negative, I'm going to put in negative 15 meters right there. Right. And then for my initial vertical component of velocity, well, I can call that now positive because it's being blasted kind of upish. So now it's positive 41.1, but whoops, it's a 1 meters per second times t, I don't know yet, minus 1/2, 9.8 meters per second squared. And I'm calling down negative, but I already took care of that with that negative sign there. And then t, I don't know again, squared. So the square that. Right, there you go. Okay, so now I have one equation with one unknown. The only thing I don't know is t. Oh boy. Guys, we're about to run smack into what situation starts with a q. Quadratic. You see it's quadratic? It's quadratic time. Maybe I should shuffle this around, put it in standard form. You guys think? So I'm going to move everything to the left. Half of 9.8, it's like 4.9. I'm going to call this 4.9 t. I'm solving for squared. I'm going to subtract this bit over, say minus 41.1 t. The negative 15 is already over there, so I'll just leave that as still negative. And that's all equal to 0. I dropped my units just to make it look a little cleaner. You guys know all these numbers have units attached to them. Okay? Do you guys see a poster over there that says quadratic formula? Or maybe some of you guys have that memorized. I can solve for t. T equals, no, careful with negative signs. Make sure you got your negative footwork all in order. Okay? So a negative would be a positive, wouldn't it? So negative b, so now it's positive 41 for me, plus or minus the square root of b squared minus 4ac, square b, you'll get positive anyway, whatever, minus 4 times a times c, which, careful with negatives, there's negatives flying all over the place. You got negatives of negatives, and like, so careful. Okay. Group that all in parentheses and say divide by 2a. Okay. Now there is a plus or minus. So the interpretation would be, if you do the minus version, you're going to go backwards in time. Right? Do you think I probably want to stick to the plus so I can go forwards in time? And there's only one like future point that it crashes into the ground. All right, so let's do that. All right, so you do open parenthesis. That I'll do plus and then a square root, and then that squared. Now I have a minus minus. Are the two negatives gonna cancel out right there? So just go ahead and do plus 4ac, then close parenthesis for the square root, close another parentheses to group the whole top together, numerator, then divide by, and then guys, for your denominator, make sure you group your denominator in parentheses also. Otherwise it doesn't all shuffle to the denominator. 2a. Okay. So as long as I typed that right, and I think I did. Oh, nope. Too many parentheses there. All right, here we go. I'm getting time is equal to 8.74 seconds. That does look reasonable. Right? That doesn't look like a crazy number, so I probably did that correctly. Right. Now, I got one more step to go. The final question really is, how far x? What is this distance x? Right. Now we're going to switch back over to horizontal. Well, guys, if I know how fast it's going across the field, this number here, and know how much time that's for, can I just do x equals v sub x times t? Boom, boom, just like that. So it's going this fast across for this much time. Okay. So let's see what's that. This many meters. Yeah, that number looks pretty reasonable too. And if you were, you guys know the other versions of this have the exact same setup, the exact same premise. So this really solves all the puzzles on that side of the paper. The other ones have multiple choice answers. So you can confirm for sure if you got it correct. All right, that is a wrap on today.